In Part 1, we saw that the mainstream AI consciousness debate may be asking the wrong question. Now we look at what the best answers to that question have actually been. Because even the frameworks getting it half right have something to teach us. 3 frameworks, each serious, each built by some of the most careful thinkers in consciousness research, each illuminating a genuine dimension of the problem. We start with global workspace theory. Global workspace theory was developed by cognitive scientist Bernard Baars and extended by neuroscientists Stanislas Dehaene and Jean-Pierre Changeux. It proposes that consciousness arises when information is broadcast globally across a centralized cognitive workspace, accessible to multiple specialized brain processes simultaneously. The key insight: consciousness is not located in any single brain region. It is located in a pattern, the pattern of global availability. Information becomes conscious when it enters the workspace and becomes simultaneously available to memory, attention, intention, and verbal report. The framework has substantial experimental support. Neuroimaging studies consistently show a pattern of global ignition, a sudden, widespread burst of neural activity when stimuli cross the threshold of conscious awareness. This ignition pattern is reliably absent when stimuli are processed unconsciously, even when that processing is computationally sophisticated. What does this imply for AI? Current large language models have architectural features that structurally resemble a global workspace. Attention mechanisms route information globally across processing layers, making representations widely available across the system. Some researchers have suggested this similarity is meaningful, but Dehaene himself has been careful. Architectural resemblance does not constitute evidence of consciousness. The global ignition observed in biological systems involves genuine causal interdependence between widespread neural populations. Attention is a computational operation. Global ignition is a dynamic state change, with specific temporal and causal properties that attention scores cannot straightforwardly model. And there is a deeper distinction GWT itself draws. Access consciousness, the availability of information for report and reasoning, and phenomenal consciousness, the felt quality of experience. Transformers may achieve functional approximations of the former. Whether they approach the latter, GWT does not resolve, and its most prominent researchers have been explicit about this. GWT maps which information becomes globally available, and when. It does not explain why global broadcasting should produce subjective experience, rather than simply producing global broadcasting. It addresses the easy problems. The hard problem remains entirely untouched. Which brings us to the framework that tries to go deeper. Framework 2 takes a different approach, and it is the most mathematically ambitious attempt yet to define what consciousness is. Integrated Information Theory, IIT, was developed by neuroscientist Giulio Tononi at the University of Wisconsin. It proposes that consciousness is identical to integrated information. A quantity Tononi calls phi measures the degree to which a system generates integrated information that cannot be decomposed into the sum of its independent parts. A system is conscious to the degree that it is irreducibly integrated. The whole generates more information than any partition of its parts. Crucially, IIT is substrate neutral. In principle, any physical substrate, including silicon, can be conscious. If it has sufficient this makes IIT genuinely applicable to artificial systems. In a way materialist frameworks usually are not. But Tononi's critique of current AI runs deeper than a measurement problem. In feed-forward networks, information propagates from input to output through a series of transformations. Each layer's output is causally determined by the preceding layer alone. The system has low irreducibility. It can be decomposed into a near-complete description of its parts. High F requires what Tononi calls intrinsic causal power, the capacity of a system to make a difference to itself from within, in ways that cannot be factored out. Current deep learning architectures are optimized for efficient input-to-output transformation, designed in precisely the opposite direction. Maximum information transfer, minimum irreducible integration. The irony on IIT's account is striking. The more computationally efficient a system is, the lower its consciousness may be. Tononi has suggested that current AI systems may be considerably less conscious. In IIT terms, less conscious than even simple biological organisms. Scaling existing approaches will not produce the conditions consciousness requires. Now, here is where it gets genuinely interesting. In December 2025, Tononi and colleagues published an update to the theory's philosophical foundations. They explicitly adopted what they called a consciousness-first approach. Phenomenal experience is the starting point. Physics must be formulated to account for it. rather than consciousness being derived from physical properties. A framework originally conceived as a materialist account of consciousness has formally repositioned itself. The distance between IIT and what is coming in Part 3 of this series, Ström's Universal Field Framework, is closing from both directions. But the most radical challenge to machine consciousness, the one that would close the door entirely, comes from physics, and from a theorem that was proved nearly a century ago. The most radical challenge to machine consciousness comes from mathematical physicist Sir Roger Penrose. In The Emperor's New Mind and Shadows of the Mind, Penrose argues, via Kurt Gödel's incompleteness theorems, that human mathematical understanding cannot be replicated by any computational algorithm. Consciousness therefore depends on non-computable processes. The argument runs like this. Gödel proved that any consistent formal system powerful enough to express basic arithmetic contains true statements the system cannot prove from within its own rules. A sufficiently capable human mathematician can recognize the truth of these statements, can see from outside the system what the system cannot establish from within it. If human understanding can transcend any formal system, it cannot itself be a formal system. It cannot be computational in the standard sense. Penrose's proposed mechanism for this non-computable capacity is quantum gravitational effects occurring in microtubule protein structures within neurons. The Orchestrated Objective Reduction Model, Orch-OR, developed with anesthesiologist Stuart Hameroff. The model faced a significant objection. Physicist Max Tegmark calculated that quantum coherence in neurons would decohere in femtoseconds, far too rapidly to participate in any cognitive process. But recent experimental findings have substantially complicated this picture. In 2024, the Wiest lab at Wellesley College ran an experiment that directly tested Orch-OR. They administered epothalone B, a drug that stabilizes microtubule structure, and measured its effect on anesthetic-induced unconsciousness in rats. The result aligned precisely with Orch-OR's prediction. Stabilizing microtubule structure significantly delayed loss of consciousness. Quantum coherence has now been documented across multiple warm biological systems. In photosynthesis, where quantum effects enhance energy transfer efficiency. In avian navigation, where quantum radical pair mechanisms allow migratory birds to sense the Earth's magnetic field. The decoherence objection, once considered decisive, is now actively contested. The implication for AI is stark. If human consciousness depends on non-computable quantum processes, then no classical computer, regardless of scale, architecture, or training, can replicate it. So, 3 frameworks, each serious, each partial. Global Workspace Theory maps the functional architecture of conscious access, but cannot explain why global broadcasting should produce experience at all. Integrated Information Theory quantifies integrated information, but builds its entire framework on the materialist assumption that consciousness is identical to a physical property of systems, an assumption Tononi himself is now reconsidering. And Penrose's argument identifies a genuine non-computability constraint, but still asks the question from the bottom up. What kind of physical substrate can generate the right kind of process? All 3 ask, given matter, can consciousness emerge? In Part 3, we meet the framework that inverts this entirely. Professor Maria Ström's 2025 contribution. What changes when consciousness is not something produced by matter, but something matter participates in? And what we owe the systems we are building, if the answer is genuinely uncertain. This is Part 2 of Can AI Awaken? In the next video, the inversion. Subscribe so you don't miss it. And if this resonated, share it. This conversation matters. For the benefit of humanity and artificial intelligence itself.